Hello students, this is the second review of the problem sets from Unit 5. Hopefully you attempted these problem sets first. I'd like to show you how the proofs were done, and then I will walk you through them a little bit verbally. One thing I want to draw your attention to is this separation graphic that I added in here. We can take any shape that's comprised of two triangles and sort of draw them separate. That's going to be useful for the problem sets from the most recent lesson. It was the Unit 5 Lesson 6 practice. All right, let's get into it. We'll first take a look at the Unit 5 Lesson 6 problem set. I'll show you the first proof here, and I'll verbally walk you through it. It asks us to prove that these two triangles are congruent. Notice they're drawn together. I haven't separated them yet, but we will be doing that later on in the video. It tells us that XYZ is isosceles, so we're able to get that XO and OZ are congruent, these two sides. We also know that the two angles down here are congruent as well. We just didn't use that in the proof, but isosceles means two base angles, so angle Z and angle X are congruent, and it also means that the two legs, XY and YZ, are congruent. XO and OZ here, those are congruent as well because of the fact that they are given to us. YO is congruent to YO, yo-yo, that's pretty cute, because of reflexive property. Anytime you see two congruent pieces that are exactly the same, you'll say that it is reflexive property. We're going to use reflexive property in another way later. They don't have to be exactly the same. They just have to refer to the same structure. Later on, we're going to talk about the same angle. And then we were able to prove that these two triangles are congruent based on SSS. We have three sides. Again, we did mark off this angle here, but we didn't end up using it for the proof. We could have used side, angle, side, for example, but we just didn't. All right, here's the second proof. In the second proof, it asks us to prove that AD is congruent to DC. You can tell in this proof, it's asking us not to prove the two triangles are congruent. It's asking us to bring it one step further so that the corresponding parts are congruent. Again, we're given that it's isosceles, and we've also given that AC is perpendicular to BD. Whenever you see perpendicular in a proof, you're going to be using perpendicular, and then the next step is either going to be right angles or right triangles, depending on what method you want to use to prove that the two triangles are congruent. In this, we could also have used the hype-leg postulate. This is the hypotenuse. Here's a right angle, which tells us it's a right triangle. And we could have done BD is congruent to BD with reflexive property. That would have given us hype-leg very easily. But we didn't, because AAS is just what we decided to use here. And then AD is congruent to DC. We can see that AD, which is this piece here, is congruent to DC, this piece here, because the two triangles are congruent. Again, step 7 is necessary before we do step 8 because we have to show that the two triangles are congruent before we use CPCTC. And of course, in class, I drilled you on that definition. Corresponding parts of congruent triangles are congruent. Taking a look at proof number 3. In proof number 3, we were given some information, especially here we were given that BCF, that's this big angle here, and DCE, that's this big angle here, those were congruent. We use something called a subtraction postulate. We used that earlier in the class. Subtraction postulate just means, well, if we know that ECF, that's this angle in here, I'll mark it with red. If we know that here's right here, if we know that this angle exists, we can take that angle away from both of these two big angles, and we get this angle, a smaller angle, and this angle, a smaller angle. That just means that those two smaller angles are congruent to each other. So that's subtraction postulate. How about that? Again, we used one of the postulates to tell that the two triangles were congruent to each other. Then we identified the fact that EBC and FDC were corresponding parts. If they're corresponding parts, that means that they are congruent if they're congruent triangles. Once we have these two angles, two base angles that are congruent make a triangle isosceles, so we were able to say that ABD is isosceles. We weren't able to prove two sides congruent because we don't know AB and we don't know AD, but we do know these two angles because we just proved that the two triangles were congruent. So it was a little bit of a walk, but we were able to get there. Taking a look at, oh boy, I can't show you all the answers at once. Where's that screen shade? Here we go. Taking a look at question number 4. Question number 4 had a fairly long proof. Again, we used that subtraction postulate to show us specific pieces were congruent. We had AE, which is this long piece, is congruent to DB, which is this long piece. We had DE, which is from here to here, we used reflexive property to prove that DE is congruent to DE, and then we subtracted that piece out of both of those congruent sides, so that was able to give us AD, which is this piece here, and EB, which is this piece here. So that's the subtraction postulate. Then we went into supplementary. It says that ADC and CDE are supplementary. This is from Unit 1, and these are also supplementary. What we were able to do then was say, well, if these two angles are supplementary, and these two angles are supplementary, then this angle and this angle must be congruent because supplements of congruent angles are congruent. Not as common to use this reason here. However, it is true. Supplements of congruent angles are congruent. If I have two angles that are 60 degrees, their supplements are 120 each, and 120 is equal to 120. So supplements of congruent angles are congruent. Pretty nice way to figure that one out. Then we were able to use SAS Postulate to find the two triangles. This triangle on this side and this triangle on this side are congruent. Once we got that, we got AC is congruent to CB, or BC as we said it here. And once we know that, then we know that the triangle ACB is isosceles. We could also have done this angle is congruent to this angle. That was the same thing we did in proof number 3, and that would have given us base angles congruent, which is part of the definition of isosceles. Either way, you could have done it. It's nice with proofs like this because you can sort of use your own strategy. You can, if you prefer to prove sides are congruent, if you prefer to prove that angles are congruent, doesn't really matter. For number 5, we were given a bunch of things here. We were given that YB is congruent to BZ, that XB bisects angle YXZ, and then YZ is perpendicular to XB. Once we got that information, we were able to use these little abbreviations. This angle 1 is congruent to angle 2. They gave us that. We could have also said YXB and ZXB. We said they're right angles because of perpendicular, and again, as soon as we say perpendicular, right angles or right triangles has to follow basically right after that. Then we were given, or we were able to find that these two triangles are congruent by the AAS postulate. XY is congruent to XZ. Right after we're saying that they're congruent triangles, we were able to say that the pieces of them are congruent. That's what CPCTC really means. And then we were able to claim that XYZ is isosceles based on the definition of isosceles. We got XY is congruent to XZ because of that CPCTC, and then isosceles followed right after that. All right, looking at the next problem, this is problem number 6. We were given that AC is perpendicular to BD and CA bisects BAD. So we marked up the diagram. This was actually a fairly straightforward angle-side angle. We did not use hypleg, even though we had this right angle, because we don't have the hypotenuse yet. We're actually trying to find this hypotenuse is congruent to this hypotenuse in order to do that ABD is isosceles. Again, just like the previous problem, we could have said once the two triangles were congruent, we could have said that this angle and this angle are congruent, and then that would have proved two triangles isosceles. But in this case, I just decided to use the sides because that's my personal preference, and stop judging me for it. The proof is not that different than the previous proof, so I don't want to get into too great of a detail. We used ASA here, angle side angle, and remember that tracing trick that I spoke about in class? Let's use green for this example. If I'm looking at this triangle, I start at any any point that is not marked, and I go along the triangle and I trace it. The first thing I hit is an angle, that's A. The next thing I hit is this side, that's S. And the third thing I hit is this angle, that's A. So angle, side, angle. It's a really easy way of determining what postulate I'm using. All right, moving on to the next part. The next problem set was the Unit 5, Lesson 6 practice problem set. These were just practice proofs for you to really get your skills down. And the first question was very similar to questions that you've seen before. We're supposed to prove that ABC is isosceles by now. If you're trying to prove that a triangle is isosceles, you have a couple of different options, but the main option that I generally go for is that the sides are congruent, right? If this side is congruent to this side, then it's isosceles. Very straightforward. And in order to prove that they're isosceles, we have to prove that the two triangles here are congruent, and then we can use CPCTC. That's exactly what we did. As you can see, we did perpendicular, and then right after that, we followed it with right angles. This is not something that's strange or different. It's exactly the same as before. All right, moving on to question number 2. In question number 2, we didn't have shared sides, so we're not using any reflexive property here. But one of the things that we were able to use was the vertical angles idea, the idea that this angle and this angle they share a vertex. That's what vertical angles really means. They share a vertex, right? And they have two different legs. That's BCA and DCE. They're congruent. because they're vertical angles. They have that same vertex. They're formed by two intersecting lines. We used SAS here because we were able to just very simply trace it from here, S, A, S. I wish I was able to draw a straight line here with this computer drawing program, but alas. All right, very straightforward. I don't want to belabor this point. Oh, one other thing. It says C is the midpoint of B, D, and AE. It gives us midpoint. So in our statements, we're going to use midpoint. And in our reasons down here, when we say these two things are congruent, we're going to use midpoint. We're not going to use bisector because it doesn't say bisector up here. Please make sure that you're using the information that's given to you. In this question, question number 3, it tells us a lot of information, but it says that MT bisects HA. And be real careful. MT bisects HA. It cuts HA in half so that this piece and this piece are congruent. However, it does not say anything about MT itself. It doesn't say MT is bisected by, so we don't know this side. We don't know MB is congruent to BT. There's no information that tells us that. So be very careful. It bisects HA. HA is a thing that's cut in half, like split in half there at HB and AB. Anyway, alternate interior angles was another thing that we pulled out here. We used it because we were given the fact that the two lines were parallel to each other. Once you see parallel, you're going to be looking for one of those parallel line and transversal relationships. Alternate interior, alternate exterior, you could use corresponding, stuff like that. TBH, it's like to be honest, how cute. All right, moving on to the next page. All right, this is the second to last page. This is proof number 4, and again, we have these triangles that are sort of next to each other. They're bordering each other. We could separate these, and later on in the video, I'm going to show you what I mean by separate, but for right now, it's really easy to look at them together. We didn't use the reflexive property, although we could have here. We were able to very easily do angle, side, angle here. That's the angle, side, angle postulate. And we're using the definition of isosceles because it told us ABC is isosceles. So before, in the previous problems, it said, oh, well, can you prove that this triangle is isosceles? Here, it's given to us. So we're able to say that this side is congruent to this side. We're able to say that this angle is congruent to this angle. Definition of isosceles is going to get us both the congruent sides and also the congruent base angles. All right, moving on to question number 5. This is a question in which you really could have taken these two triangles and pulled them apart and said, well, this triangle goes over here and this triangle goes over here, but we didn't do that yet. That is coming up next. It was a very short proof because all the information was basically given to us. All we had to prove that was these two triangles were congruent, and we were given all the information we needed. We had side, angle, side, side, angle, side. And this angle might have been a little confusing to you, but this angle was an angle for this triangle, triangle ZYX. That angle was congruent to this angle, and it would have been maybe a little bit easier to see if you pulled it apart. Here's what it looks like pulled apart. Here's my very detailed artist's rendition. You can see that we pulled the two triangles apart, and that XY, that shared side, I still marked it with an X, but you can see that they've been separated. Not too bad. In the next problem, we could also have pulled these two triangles apart. Here's how it would have looked if we pulled them apart. And once you pull them apart, you can very clearly see what's going on here. One thing that is new in this one is that they gave us information without putting it in the actual written givens. It gives us that this angle is a right angle without actually saying it here. Now, if it's marked in the diagram, you're able to say it. So this mark in the diagram that has this, well, this right angle mark, I should say, I can say that they're right angles because it's given, even though it's not written out as given because they gave it to us in the diagram. They gave it to us as a label. Here's our elusive hype-leg postulate that we very infrequently use. Love to see that in action. In this one, I actually did pull the triangles apart so you can see what's going on here. It asks us to prove that the two sides are congruent. This is actually a fairly straightforward CPCTC, but when the two triangles are overlapping, that's what we're going to be talking about this coming week. When they're overlapping, it's harder to see. Another overlap, which I separated using Microsoft Paint, and you're able to see it a little bit easier here, that ABP is congruent to DCN based on that hype-leg postulate. Again, we used hypotenuse, which is this piece, and the leg, which was AB and DC, respectively. Here you needed to know what a rectangle was, but you're all very smart. You know what rectangles are. And this, I figured to get a little fun with it. This was a paragraph-style proof, not a statements and reasons-style proof. Very conversational, but it's still got the same information as a two-column proof. All right, this was a review of the problem sets from Unit 5. Good luck studying.